Hello everyone. In this lecture, let us look at how to design a photonic integrated waveguide. So, we have looked at waveguide properties in various aspects and various configuration. The fundamental or let us say very basic waveguide structure is a slab waveguide. So, we looked at a sandwich of layers. So, we have a core waveguide and then surrounded by a lower refractive index medium which is called cladding. So, we looked at an infinitely thin waveguide. So, that means the light is confined vertically by index contrast and laterally it extends. So, we have a pretty good understanding of that, but in practice we do not use this kind of slab waveguide. We use rectangular type of waveguide. So, that means you have both x and y, right. So, you have boundary both in x and y. So, the confinement in the vertical direction is by the index contrast we have, and also in the transverse direction you also have index confinement. So, in this case how do we understand light propagation? So far we had the z axis, along the z axis how the light propagates, but now we are going to turn it and then say the z axis is inside or outside the screen, but then you have x y region to try to understand how the light or the field is going to be there. So, we already looked at how the field profile would look like, and we also understood the propagation constant and associated with the transverse and the longitudinal direction, but now everything is going to change. So, now we are going to look into both x and y aspect. So, we made our problem reasonably simple in the earlier lectures by having y axis infinite, right. So, there is no boundary. So, now we are going to put a boundary to x and y. So, when you put a boundary, how are we going to understand this? And more importantly, this is the fundamental structure that we use in integrated optics. In all the circuits we will have some sort of rectangular structure, not just in photonic ICs, but also semiconductor lasers, for example. So, the light confinement in semiconductor lasers is through this two dimensional confinement. So, you have vertical x and horizontal y, the other way around as well, but you have confinement both in x and y direction. So, that means there is a boundary there. So, it is important for us to understand how one can define the conditions, the propagation conditions, and also the field profile. So, how my electric field is going to look along x and how my electric field is going to look along y. So, if you remember in the guided wave discussion, we took dou E or dou H over dou Y to be 0, right, because there is no boundary at all. So, y axis is nothing to say, but in this case that is not going to be. So, here there is a boundary there. So, the tangential component of E field and H field, there should be a continuity boundary condition now. So, those are all the new addition that you have to consider when you are talking about two dimensional structure now. So, this was earlier considered to be very hard problem to solve. It is still not trivial to solve for this field in a rectangular geometry. It is not trivial at all if you want to do it in an analytical sense, but there are some approximations you can do. You can take this two dimensional case and make it one dimensional. So, you can flatten in along x or flatten along y in order to make this problem reasonably easy to attempt. So, the pioneering work was done by Marcatelli. So, he came up with ways of looking at this two dimensional structure. and how one can define the boundary conditions, because the problem here is the boundary condition. When you have two interfaces, you do not have any problem, it is nicely defined, but then the moment you put another interface, it becomes tricky. So, you might be wondering what is tricky about it. We will see that in a minute. Let us look at integrated optical waveguide design now. Let us jump into it. So, any rectangular waveguide, so we saw in the introductory classes, right, the different type of waveguides. So, we could have a very simple, let us say something like a buried waveguide like this. So, there is N1 and there is N2. This is one type of structure, and the other type of structure is completely buried, where this is N1, this is N2. And you could have another type of structure where you could have N1 and N2. There is one more where you could have something like this. So, N1 in all cases is greater than N2. So, these are all different type of rectangular waveguides, right. So, these are all different type of rectangular waveguides. So, what is very difficult about these structures, right. So, I mentioned something about the boundary condition, right. So, boundary condition for these waveguides are not that clear, right. It's coupled. Why is that, right. So, that is what we want to understand here. So, before that, everything is now in 2 dimension, you see here. So, we have y and we have x. So, because we have a boundary in y, now the field would also be similar. So, you will have a field along x and a field along y. So, this is how our field is going to be. So, that means that you need to find the solution along x direction and solution along y direction. So, you need to have this in mind. And now, let us look at what is tricky about this particular structure. Let's look at an embedded structure, which is much easier to look at. So, I can take a waveguide like this. So, it has a certain refractive index, right. And now, if I want to dissociate into different components, right. So, let me say this is y axis and this is x axis, right. So, if I look at this, then what I see here is I can have a region N1, okay, and I could have multiple possibilities here, and I could have N2 here, and that could be N3, it could be N4 and N5. So, these are all the different regions or different boundaries that we should consider when solving for a waveguide here, right. So, if you consider this is my rectangular waveguide, but then if you want to put the boundary condition, now we have multiple domains here. So, we along the x and along y. So, the problem here is between if you look at the region N1, N2 and N3, these are all reasonably easy to define the boundary condition. It is straightforward, right, because they resemble the thin planar waveguide geometry. Similarly, N5 and N4 as well, right. So, their boundary conditions are nicely defined. But how about the corners, this corner regions, this region, this region, this region and this region. So, here things become very difficult to define, Why is that? Because there in all these 4 regions x and y are coupled now. So, you cannot write the boundary condition just for x or y. So, x and y are dependent, right. So, the solution will also be x and y dependent. So, this is where the problem gets really interesting. And the other important thing to notice here is we have x and y, right, because you have x and y, the way we designate any field would also be little different. For example, if you have a TE mode, right, so you have an electric field E, right. So, it is along y and it will have the mode number m and n, for example. Okay. So, this is one mode where it is confined along y direction, right. This is TE mode. So, you have electric field along this y direction, and you could also have x, right, along m and n. In this case it is parallel to x axis. All right. So, these are all different notations that we use to designate various fields that you have in this particular rectangular geometry. So, this is a little different from what we saw in a slab waveguide. So, in order to solve for this, you need to formulate a boundary value problem, right. So, this is something that is reasonably straightforward to do, the formulation at least here. So, we looked at this waveguide and say, okay, so if you want to have a solution to this, then probably that particular wave, right, should propagate through this with a certain eigenvalue, that is beta, for that particular solution, right, and you want this solution to be much above the cutoff. So, we saw the cutoff condition in our slab waveguides, right. So, you want this waveguide to propagate this mode to propagate through this waveguide. So, it should be greater than the cutoff. All right. So, let us look at right now let us ignore this the corners, right. So, we will ignore this corners and we will only consider the uncoupled ones, right. So, there is no coupling between the x, y and z components, right, let us say, and if that is the case, then we can write the wave equation as a scalar form, right, and if chi is your wave, you could write something like this, d dou y square plus k naught square n squared x comma y minus beta square chi equal to 0. So, this is your scalar wave equation, right. So, we are writing this because it is uncoupled, let us say there is no coupling between x, y and z, and in this case k naught is nothing but free space wave vector and beta is the propagation constant. But we still do not know what this propagation constant is, right. So, it has a certain propagation constant, you do not know what it is, because that is what we want to find out, right, and n x comma y is nothing but refractive index, right. So, this is similar to what we have seen earlier. So, there is nothing new in it, but this is where we have to start this, right. So, we need to start everything with this wave equation. So, now let us look at the solution itself. So, the chi is the the propagating wave here, right. So, what could be the solution to this, right. The solution for this will be as a function of x and y, right. So, it is rather straightforward to do, that is something that we saw earlier. you can do it x of x, y of y, right. So, where this x of x is nothing but amplitude distribution along x, right, and similarly y is amplitude distribution along y, right. So, similarly this one is amplitude along y direction. Okay. So, this is very very straightforward. This is how we see the solution, and here again the solution here, right, particularly let us say in this particular guided region, this N1, right. So, N1 is where you have the light propagating, there you will have a sinusoidal solution, right. So, you will have sinusoidal solution wherever light is propagating, and outside it should have a decaying solution, right. So, you want to have that sinusoidal solution in N1, but in N2 and N3 region you should have a decaying solution, let us say, right, for the light that is oriented along x direction. Okay. So, now your field, right. So, your general form of the solution. So, general form of the solution chi x comma y will be chi naught e to the power minus j k x 1 x plus k x k x I in this case k y I y into e to the power minus j beta z. Okay. So, plus some constant here, all right. So, this is something we also seen earlier. So, k x I k y I depends on which region you are, right. So, when you take this region 1, 2, 3, 4 and 5, right. So, in this case it will be k x 1 and k y 1, here it will be k x 4, right, k y 4, right. Similarly, here k x 3 and k y 3. So, based on the region that you work with. So, this is k x I and k y I are nothing but propagation constant, right. Constant in respective regions, right, 1 to 5, right. So, this is something that one can take, all right. So, now the propagation constant along x would be k x 1, k x 4 and k x 5, right, when you take 1, 4 and 5, right. And this propagation constant should be identical, right, and independent of y, all right. So, if you are taking along x, right. So, your k x I k x 1, k x 4 and k x 5, right. So, this is in region 1, 4 and 5, right. So, this must be identical, this all should be identical and independent of y. Okay. So, this is for x propagation constant, right. So, this is x propagation constant. So, all of this should be here. So, similarly you can do it for y as well. So, this is something you should keep in mind, because the wave is distributed between 1, 4 and 5, right. And similarly, if you are taking y direction, so 1, 2 and 4 in that direction, y component should all be identical. So, that is how you will keep that particular energy going through. You remember we in a slab waveguide, if you want the mode to propagate, the propagation constant should be identical, right, between the two layers, right. So, this is something we saw. Again, we are using the same condition here, we have not invented anything new here, but the condition is here there are two directions that we have to take into account, x and y. So, now we can modify this wave equation, right, that you could do this dou square x by dou x plus dou squared y by dou y plus k naught square n squared x comma y minus beta squared equal to 0. This is something that we know already. So, we need to do some rearranging here. So, if we do that rearranging, dou square x by dou x squared, right, in this case squared should be equal to minus k naught squared n squared x comma y plus beta squared minus dou squared y by dou y squared is equal to, we are going to introduce separation constant here, minus k x squared. Okay. Perhaps I should use a different color here, because all right. So, similarly we could, so this is nothing but this is separation constant. Okay. Nothing new. So, similarly we can do for our y as well. So, this is equation, can keep this as 2, this is equation 3 and this is equation 4. Okay. So, now we can write the same thing for y as well, right. So, we can solve for y function. So, dou squared y by dou squared equal to minus k naught squared n squared x comma y plus beta squared. So, now here I can write this as minus k x squared, okay, which is equal to minus k y squared. Again, this is just the separation constant. Okay. So, this is our equation 5. So, what we are going to consider here is the refractive index, that n x comma y that we have, right. So, this is uniform within the region of interest, right. So, here we have 1, 2, 3, 4 and 5, right. So, at least in 1 is where we are interested in, because in region 1 is where we have our core, right. But this core refractive index is uniform within the region, and the rest of the region it is uniform, but less than what you have in region 1, right. So, we will use what we call a step index refractive index, right. So, that means you will have something like this. So, this is region 1, region 4 and region 5, let us say. So, there is a n1 what we have here. So, this is the refractive index within the region here. So, now n x comma y will be equal to n1. So, if n1 is greater than the rest of the region, so that is what we have agreed so far, then the possible solution, right, allowed solution will be of this kind. So, x of x will be a cos, in this case k x times x plus phi of x. Similarly, for y you will have b cos k y times y plus phi of y. So, in this case phi of x and phi of y are nothing but phase constants that are adjusted to match the boundary condition. Okay. So, if you remember, again I want to go back to our a simple planar waveguide discussion here. We had reflection from the boundaries, right. So, we had the phase accumulation because of reflection from region 1 to 2 and region 1 to 3, right. So, phi 2 phi 3 for the phase matching. So, in this case phi of x and phi of y are similar, but then one is associated with x boundary and the other one is towards y boundary. Okay. So, now the separation constants that we have kx and ky should satisfy, right. The separation constant should satisfy the boundary condition here, right, that is given by beta. So, k naught square n 1 square minus kx minus ky square. So, this is the condition that it should satisfy. Okay. This is coming from our equation number 5 itself, right. So, so this is from 5. So, this should be satisfied. So, these two equations we call this equation number 6 and this is equation number 7. All right. So, now you can clearly see the similarity with the slab waveguide discussion that we had in the earlier lectures, right. But then the only thing here is everything is double now, everything is with x and y, right. So, the outside the code the guided mode solution should at least have one component which is exponentially decaying. So, that is an important requirement in order to confine the light. So, let us look at the cross section again here. Okay. So, this is where you have the light that is getting confined. So, outside all these region, for the moment let us not worry about this corners, the corners we will bring it up as we mature the understanding here. So, all the dotted regions that you see here, right. So, the dotted region should have at least one component that is decaying. So, for example, if you take the x component along 1, 2 and 3, all those components should be oscillating in one of the coordinates, but then for 2 and 3 should have at least decaying solution in the other coordinates. Okay. So, that is very important. So, similarly for 1, 4 and 5, right, you will have oscillating solutions in let us say in y direction, right, but in x direction you should have decaying solution for 4 and 5. So, the required condition here is so let me do that. Outside the core, right, outside the core, in this case region 1, the guided mode, this is very important, not for all the modes, for the guided mode solution there must be at least one exponential decaying component. Okay. So, this is something important that we should all keep in mind, because you have x and y, right. So, if you take a simple thin film planar waveguide understanding, it will be all clear, because you will have oscillating solution here and decaying outside, right. So, that is true in this simple geometry, but then you also have a vertical component here, right, along x. So, in this case again you will have a decaying solution here an oscillating solution and decaying solution. Alright. So, as you can see here, when it is oscillating along y direction, in this case it will be oscillating here, here and here, okay. But then when you look at x component, it is decaying, alright. So, you should at least have one decaying solution in order to keep this mode in. So, we will visualize this as we progress, but keep this in mind. We will revisit this particular statement later on in the lecture, alright. So, let us consider a solution in region 3, for example, okay. So, region 1 is where we have our waveguide propagating mode is sitting, but let us look at region 3. So, region 3 is where you should have something decaying, alright. So, let us look at region 3. So, let me draw this again, so that we keep this in mind, 1, 3, 4 and 5, alright. So, let us consider region 3, okay. In this region, right, where we need to match the boundary condition along y, right. So, you have your y and you have x, right. So, for x greater than 0, if this is there, we can say x greater than 0. How are we going to understand this, all right. So, we can right away write the wave equation, right. So, dou square chi divided by dou x square minus k y squared chi plus k naught squared n 3 squared minus beta squared chi be equal to 0. So, this is the wave equation in region 3, right. So, this is the wave equation in region 3, alright. So, this is what you have. So, now if you substitute this the equation 7 here, right. So, you have 7 into 8 now. So, we are going to do this. If you do that, then what you will end up with is the right hand side of this, right, and dou squared divided by x should be minus k naught squared n 3 squared minus beta squared minus ky squared, which is equal to, we just do some rearranging here, k naught squared n 1 squared minus k naught squared n 3 squared minus kx squared. So, this is equation 9, alright. So, this has the solution. So, this the solution here, right. Let us say this is chi 3, right. So, you have chi 3 x around x direction, right, will be, I'll put it as x here, e to the power minus gamma x for x greater than 0. So, this is actually the solution to this, alright. So, what is gamma 3 here? Under root k naught squared n 1 squared minus n 3 squared minus kx squared. So, this is again something familiar for us, right. We have seen this decaying. So, how this would decay is because you have an imaginary solution. So, that means it is decaying here. So, this is the decay constant gamma that we have seen here. So, now we have seen how this field along x is going to look like. So, we can put field along x and y now together, right. So, let us put this how the field is going to look both in x and y. Okay. So let us go back and look at this particular structure again. So we just looked at this x component, right, and along y it should have an oscillating solution, right. So all the solution along y will be oscillating for 1, 2 and 3. Okay. But then for 3 the y component of the solution will be decaying. All right. So let's write the total field here. So total field chi of x comma y now is nothing but some constant c cos ky plus phi of y. So this is our oscillating component along y direction, right. So along y direction you will have oscillating for 1, 2 and 3, all the 3 will have oscillating solution. Okay. But then the component that we just found for x, right. So e to the power minus comma c times x. So this is for x greater than 0 and then y between 0 and let us say some with b. So we can put b here, let us say. All right. So within this particular region, right, we have a solution for our field, right, in this region 3. So we can continue and do this for all the other regions as well. So the similar set of solutions we can do it for other regions, right, x and y. So let us just write for simplicity for 2, 4, 2, 4 and 5 as well. Okay. So 2, 4 and 5 just to give us some understanding on this, right. So x2 will be e power gamma 2 x plus a for x less than minus a. So a is nothing but the width here. Okay. So the dimensions is a and b, and then you could have y4 of y is nothing but e to the power of minus of 4 y times b. This is for y greater than b, and then we have y region 5 which is e to the power comma 5 y for y less than 0. Okay. So these are all the 3 different region components for x and y. So what is gamma 2, 4 and 5? That will follow the similar trend that we had for 3 here, right. So this is 3 here. So let us do that as well. So gamma 2 is nothing but k naught squared n1 squared minus n2 squared minus kx squared, gamma 4 is root of k naught squared n1 squared minus n4 squared plus ky squared, gamma 5 is nothing but k naught squared n1 squared n5 squared minus ky squared. So these are all the decay constants. So this is all nothing but decay constants. So as we already discussed in the earlier lectures, so this decay that you see from the interface, right, it follows this gamma factor, and this gamma strongly depends on the refractive index contrast between the two, right. It could be n1 to n2 or n1 to n4 or n1 to n5. So difference between the core refractive index and the index that is covering this, right. So the higher the refractive index contrast, right, the lower is the range. For example, you could have this and you could have this. This is as a function of x or y. So here let us say this is gamma 1, no, this will confuse you. Let me pick 2 colors now, right. So there are 2 gammas here, a red one and then I will pick a blue one here, right. So now the red gamma that you have is greater than the blue gamma. So, when you have greater index contrast, right, the difference between the two, then you are also going to make it decay faster. So, that will ensure that you have high field confinement. So, this is one of the reason why we try to use high refractive index contrast mediums in order to confine light tightly. All right. So, we will see this on our different waveguide platforms, but remember about this. So, now we have just an example of this the optical field is in different regions, but let us have the two components distributed in all the different regions that we saw. All right. So, let's take this, right. We will look at the different regions here. This is region 1, and then we have region 2, this is region 3, and this is region 4 and region 5. Okay. So, this is the regions that we are looking at. For the central region, we will have oscillating solution for both x and y. So, that solution will look something like that, kx x plus phi x. Similarly, for y, ky y plus phi y. And let us look at 3, so which is something that we just saw. So, cos ky y plus phi y, and your you will have a decay along x, right. So, that means e to the power minus gamma 3 times x. So, here this is y and this is x. Okay. So, just keep that in mind. So, now let us look at y, right. So, y again it is quite trivial that you should have oscillating solution along y, right. So, cos ky y plus phi of y, but now it should decay here, right. So, e to the power gamma 2 x plus a. So, because this is a and let us say this is b. All right. So, this is 0. All right. So, this is 1. So, let us look at region 4. Region 4 you will have oscillation along x. So, you can write it here, and also I can write this here as well. Okay. So, now it is going to be decaying along y direction. So, e to the power minus gamma 4 y minus b, and here e to the power gamma 5 times y. Okay. And similarly for the edges. So, that is where the tricky part is, because around the edges you will have only decaying solution. Okay. So, e to the power minus gamma 3 x. So, that is coming from here, e to the power minus gamma 4 y minus b, right. So, you have the y component coming from here, the x component coming from here. So, it takes the boundary or the solution from the neighborhood to do this, because there is no clear boundary condition you can apply here. This is coupled. So, similarly here e to the power of minus gamma 3 x and e to the power gamma 5 times y, and at the bottom we have e to the power of minus gamma 4 y minus b, e to the power of gamma 2 x plus a, and here e to the power of gamma 5 y and e to the power gamma 2 x plus a. So, now the corner regions got only decaying solution, you will not have any field here at all. So, this is what the challenge is about when you are doing analytical solution to this. All right. So, So, let us quickly look at how you could solve this boundary value problem, right, once we understand this. Okay. So, with this understanding of field, both oscillating field and decaying field that you have inside this region, right, one should be able to identify where the field is, right, and what is the amplitude of these fields that one could have, right. So, those are all the things you can find out with the understanding we have so far. But the next step is to identify this beta. The primarily we are chasing the propagation constant. We need to find this propagation constant from the solution that we have. Right now we have just found how the solution is going to look, but then we have to quantify that. So, that quantification comes from the propagation constant that we have. So, we have kx and ky, right, that you could find out, but then as a complete mode, right. So, individual components we have, but then as a whole it has to propagate with one single propagation constant. So, we need to then solve this using boundary value approach, right. So, let us look at that in the next lecture. Thank you very much.